Now, if we look at a power series which has powers of x in it, then this power series can only be constant 0 if all the coefficients are 0. So what we have to do now in the following, we have to combine the coefficients of all the three different terms, and we have to look at the single powers of x, x to the naught, x to the 1, x squared, and we have to make sure that the coefficients in front of these powers are all 0. You can either, like I said, combine the three sums into one sum and then take a look at this power series, or you can simply go through the powers of x and see if you can spot a pattern in this solution. And that's what I did here. So I start with x to the naught with the constant terms and then continue with x to the 1 and so on and so on. So let us start with x to the naught. Where do we get x to the naught terms in our sum? You find the equation that we have to solve at the top of the page again. Let's start from the left. The sum on the left-hand side, which starts at n equal to 2, but has a term x to the n minus 2 in it, well, this contributes an x to the naught term if n is 2. And what do we get then? If n is 2, then we get 2 times 1 times a2 times x to the naught. So this gives 2 times a2. The sum in the middle, well, here we start with n equal to 1. So we actually start with x to the 1. This sum doesn't contain any x to the naught term, so we don't get any contribution there. But the sum on the right starts with n is equal to 0 and has an x to the n. So we get a naught times x to the naught as a power x to the naught from this sum. So in terms of the constant terms, the 0th power of x, our equation we have to solve is 0 is equal to 2 times a2 plus a naught. Or we can rewrite this as a2 is minus a naught over 2. Let's take a look at the linear terms. So powers of x, x to the 1. Again, start with the sum on the left. If we set n is equal to 3, then x to the 3 minus 2 gives us an x to the 1. So we get 3 times 2 times a3 x to the 1 from this term. Now the sum in the middle also contributes, namely with n is equal to 1, 1 times a1. And the sum on the right contributes with n is equal to 1, a1 times x to the 1. So in order to make the coefficients in front of the x to the 1 term overall 0, we have to solve the equation 6 times a3 plus a1 is 0. Or we can rewrite this as a3 is minus a1 over 3. And so we go through all of these terms. Maybe let's have a look at one more step. If we look at the x squared terms, then in the sum on the left, we have to set n is equal to 4. So we get 4 times 3 times a4 times x squared. For the sum in the middle, we have to set n is equal to 2. So we get 2 times a2 times x squared. The sum on the right, we have to set n is equal to 2. We get a2 times x squared. So the overall coefficient, or the combined coefficient in front of the x squared, is 12a4 plus 2a2 plus a2. Or we can write this as a4 is equal to minus a2 over 4. And now you can already spot the pattern. You might want to check this again on the next term. So you get a5 is minus a3 over 5, if you do this carefully, and so on and so on and so on. So we have a formula for our coefficients, an. And this formula is the following. An is minus an minus 2 divided by n. So how can we find the coefficients from this formula? An is minus an minus 2 over n. Well, we have to start somewhere. So we first of all need to determine a0 and a1. And we actually can do this in this example. Because as we discussed earlier, a0 is nothing else but the value of the function y at 0, and a1 is just a derivative. This was in the part about the Taylor series. So now we can actually use our initial data and get values for a0 and a1. Since y at 0 is meant to be 1, we get that a0 is 1. And since y prime at 0 is meant to be 0, we get a1 is equal to 0. If we didn't have the initial data, then we would have to leave a0 and a1 as parameters in our solution, and we would compute the general solution of the ODE. But since we have initial values, we can use them. And now, step by step, we can compute the values a2, a3, a4, and so on. a2 is minus a0 over 2, so that's just minus 1/2. a3 is minus a1 over 3, this is 0. and so on and so on and so on. And you already see all the coefficients with an odd index, they turn out to be 0. Well, this is very easy to check, right? Because our formula involves always terms an and terms an minus 2. Now, if an minus 2 is 0, then an must be 0. And if you like to do proof by induction, this implies that if a1 is 0, then all the coefficients an with an odd index, we can write a2k plus 1, they must be 0 for all values of k. So this is quite easy. It is a bit more difficult to find a general formula for the coefficients with an even index. I write those as a2k, because 2k is always an even number. But we can do this by looking at a few steps of this recursion, so this stepwise process of computing the numbers. We know that a2k is 1 over 2k times a to k minus 2 with a minus sign. And now I use the formula again for a2k minus 2. a2k minus 2 is 1 over 2k minus 2 times a2k minus 4 with a minus sign, and so on and so on. And if I go back all the way to a0, then in the end, I get that a2k is a product of 1 over 2k, 1 over 2k minus 2, and so on, until we reach 1 over 4 and 1 over 2. All of these numbers are actually negative. And then at the end, we have a0. Now, a0 is 1, so this cancels. We can actually simplify this product even further by counting the terms and looking at them in more detail. There are k terms that we're multiplying, so k factors. Each of these factors has a minus sign, which gives us a minus 1 to the k. All of these factors are even, or well, 1 over an even number. So this means we're actually multiplying 1/2 k times. So we get a 1 over 2 to the k. And now if we were to divide each of the numbers by 1/2, what are we actually left with? Well, we get 1 over k times 1 over k minus 1 times 1 over k minus 2, and so on, all the way down to 1 over 2 times 1 over 1, which is nothing else but k factorial. So the whole product actually simplifies to minus 1 to the k, 1 over 2 to the k, and 1 over k factorial. So this is an explicit formula for the coefficient a2k, all the coefficients with an even index. And there we have it. This is the solution of the differential equation as we found it. So we can write our solution y of x as an infinite series, as a power series, an x to the n, where n goes from 0 to infinity. Now, this series only contains even powers, so I set n equal to 2k again, which means I get a series where k runs from 0 to infinity, minus 1 to the k, divided by 2k k factorial, times x to the 2k. What do we do with this solution? Well, in this example, it turns out we can actually compute the function. But in general, this is where you would have to stop. In general, you can't go any further. You have your solution as a series. What you can do, of course, is you can just consider finitely many terms of this series, just like we did for the exponential function. So if you just consider the first n terms, say n is 8 or 10, then you can hope that this polynomial that you get gives you a good approximation to the solution. For our example, though, we can do better. We can actually simplify the terms in our series a little bit. It turns out we can group the minus 1 to the k, x to the 2k, and the 1 over 2 to the k into one term, which reads minus x squared over 2 to the k. So the series now becomes minus x squared over 2, all of this to the k, divided by k factorial. Now this series looks quite familiar. We've got something to the k divided by k factorial. And this is very similar to the exponential, to the series of the exponential function that we saw in the example. And indeed, we can use this. If we just set a new variable z as minus x squared over 2, then indeed our series simply becomes the series k from 0 to infinity z to the k over k factorial. And we know what this is from the example. That's the exponential of z. So now we make a little back substitution. We know what z is. Z is minus x squared over 2. So the solution is actually y of x, the exponential of minus x squared over 2. Well, Now we've got a function in an explicit form, y of x is some function of x, an exponential function. We can actually check that it is a solution of the equation. You can easily check that the initial conditions are satisfied by this function. In order to check that the ODE is satisfied, we have to compute the derivatives again. So we differentiate y of x twice. If we differentiate it once, well, we have to use the chain rule. The derivative of the exponential function is just the exponential function again, so we get exponential of minus x squared over 2. And then we have to multiply this by the inner derivative according to the chain rule. So we have to differentiate minus x squared over 2 with respect to x, and we get minus x. So the derivative y prime of x is the exponential of minus x squared over 2 times minus x. The second derivative, well, we get this by differentiating this again. Now we have to use the chain rule and the product rule. So we differentiate the first term, we already know what this is, and multiply it by minus x again, so we get the exponential of minus x squared over 2 times x squared, because minus x times minus x is x squared. And now we differentiate the minus x with respect to x. This gives us a minus 1, and we add this, we multiply this by exponential function, and we add this to the first term, and then we get the second derivative of y, as you can see on the slide. And now if we compare these terms, we find that in fact the second derivative is equal to minus y and minus x times y prime, and if you bring y and x times y prime to the other side, this is exactly the differential equation that we wanted to solve. So y of x is indeed a solution. So there you have it. This is how it works. Here's a little summary for you. If you are given an ODE and you don't quite know how to solve it, either because you've forgotten about the method or you never learned any method for it, then you can try to look for a solution of the ODE in form of a power series. Simply set y of x as a power series an times x minus x naught to the n, where n goes from 0 to infinity. X naught is a number you can choose. If you are given initial data or initial conditions, then choose x naught as the point where the initial data is provided. If you are not given any initial conditions, then simply set x naught equal to 0, because this is usually the easiest case. And then you substitute your power series into your differential equation, which means you have to differentiate the power series. Then you compare coefficients in front of powers of x, which gives you a system of equations for the coefficients an. You have infinitely many coefficients, so this is an infinitely many dimensional system of equations, if you like. Usually this system can be solved by recursion, and in some cases it's even possible to derive an explicit formula for the coefficients an. If this is possible, then this is a good result. In a few exceptional cases, you can then even turn your power series back into a function y of x again, just like we saw in the example. Usually this might not be possible. In this case, you can at least use the power series solution to approximate the real solution of the ODE, just by considering only a finite number of terms in your power series. Thank you very much.